Muted.
All right, hello. Good afternoon, everyone. Thanks for joining. We're going to go ahead and get started now. Thanks for waiting. It looks like we've got all of the attendees in the meeting now. So I want to thank you all for joining this third webinar in our series on small diameter copper tube fin heat exchangers. In this session, we're going to be specifically talking about the effective design of small diameter copper tube fin heat exchangers. So my name is Dennis Nasuda, and I'm joined by my colleague Daniel Basilar, who you'll recognize from the last two webinars that we presented. We work with Optimized Thermal Systems. If you haven't joined the first two webinars, here's a bit of an introduction. We are a company that does consulting work and experimental work in the HVAC&R industry. And we're conducting this webinar series with our partners from the International Copper Association, which is an organization that seeks to promote the use of copper. So before we begin, I just want to cover a couple of housekeeping items. The first item is that this session will be recorded. So if you miss any content or want to go back at a later date to review what we've discussed, we'll distribute that recording by email afterwards. And if you want to share that to any of your colleagues or anyone interested, you'll be free to do so. The second item is we'll be taking some questions at the end of the session. So I'll just ask that you remain muted through the duration of the session and submit your questions using the chat feature on GoToMeeting. And then at the end, we'll be able to look through all of those questions and provide you with answers. And then we'll also be providing a summary of all questions and answers from the entire webinar series by email afterwards. And then the last thing is you should have received a demonstration version of our Coil Designer software in email to join this session. And that will allow you to download and use that software for the next month or so to design and simulate small diameter tube fin heat exchangers. You'll also receive another link at the conclusion of the webinar series to download it, but it should already be in your inbox if you've found your way to this webinar. So as a brief overview, we're just going to talk about some introduction and background information to motivate this discussion. We'll go into some information about the fundamentals of designing with small diameter tube fin heat exchangers, the importance of modeling and simulation in the design process for heat exchangers, and then we'll go on to show some applications where we demonstrate how a heat exchanger is modeled, validated against experimental data, and then we'll go through sort of an example case study of our design process for developing a 5mm heat exchanger design. And at the end, as I mentioned, we'll take some questions from the audience. So let's go ahead and get started. So the first question we want to ask here is, why does heat exchanger design really matter? And we know that there are a number of pressures that are driving HVAC&R systems to improve their energy efficiency, reduce their environmental impacts, and reduce cost. We know that heat exchangers are really fundamental components in these systems, and as such, they allow us to effect change in each of these categories by improving the design of the heat exchangers. And as we learned from our first webinar, we've seen evidence that the small diameter tube fin heat exchanger in particular has the ability to improve energy efficiency of the heat exchanger and therefore the entire vapor compression cycle, and has the ability to reduce the internal volume, which can help us to reduce charge and reduce our environmental impacts, and the reduced material consumption can lead to cost savings. So I want to begin by talking about how we design heat exchangers. Conventionally, there's a lot of trial and error in the industry. We typically have situations where we may have an existing design of a heat exchanger that is successful and meets our requirements, but we have a new task where we need to develop a different product that may have some different percentage of heat load of that original design, for example, or we may have a need to reduce cost of an existing design. And based on our knowledge and experience, we can do some guesswork and come up with an initial design, build a prototype and test it, and then really determine whether or not that prototype meets our requirements. If so, then we can produce that design, but if not, we need to redesign the heat exchanger and go back to the drawing board with a new new concept that has to be tested again. And this process works well when we have a good understanding of heat exchanger geometries, if we're always working with the same surfaces and same materials. But when we want to explore a heat exchanger with a new tube diameter or new fin surface, we may not have the knowledge or the experience on in order to know what to expect in terms of the performance of that heat exchanger. So that's going to lead us to needing to do excessive iteration. And of course, there are hand calculations that can be performed. We can use Excel. We can use different rules of thumb that may exist in the industry to give us a little bit of information about a heat exchanger design before we go and prototype it. And that may give us knowledge of roughly how many tubes or roughly how much surface area might be required to do a certain job. But ultimately, we're led to the same situation where these tools can be may not be as accurate as we desire when we go into the testing phase. And if we want to evaluate multiple designs, we may end up needing to spend a whole lot of time in this design process. So what we'll be talking about in this session is really design through the use of simulation tools, and how this will help us to develop more effective designs with small diameter tubes, which may be new to some of us, so we can come up with designs that work the first time around. So in the simulation process, I'm showing here that there's an initial design process that takes place entirely in the simulation environment, where we can design a heat exchanger, simulate that design, and really iterate through that process on our computer very quickly to determine if the design will be suitable before we go into the prototyping and testing phase. And this allows us to save a lot of time from a lot of lab time, and it allows us to explore a much larger design space. So, when we look at this simulation process, we're able to parameterize the heat exchanger and run larger numbers of simulations, and we're also able to automate that whole process by using optimization tools to come up with the preferred design before we get into the testing phase. And when we have accurate design tools that we can trust and give us reliable results, that means we need to do less iteration when we go to the lab, and more often than not, we come up with a design that is going to be suitable the first time around without having to build multiple prototypes. So this is really the focus of what we want to talk about today, is leveraging the simulation tools that are available in order to help us in the design process when we move to smaller diameter tube fin heat exchangers. So there's a bit more motivation. I want to ask the question of how many ways are there for us to design a tube fin heat exchanger? So this is just a very simple example, but we could think of at least 6 different tube diameters ranging from 5 millimeters up to 1/2 inch. We could think of 6 different fin types. That might be flat fins, wavy fins, slit fins, other enhancements, and we can certainly imagine more. There are continuous variables where there really could be infinitely many options to us, such as tube length, fin density. We could pick really any value, but we can imagine at least 10 different fin densities, tube lengths, 10 different pitches between the tubes in each direction. We could come up with a number of different circuitry configurations, but this is going to already produce something like 3.6 million designs. So it's a really comprehensive design space, and we've really come up with a kind of coarse assessment of all of our, coarse parameterization of all our variables here. And just to kind of put some visualization to that, this is about 50 to 60,000 designs plotted in terms of their material cost on the x-axis and air pressure drop on the y-axis. And you can see these designs vary by an order of magnitude in terms of cost, 2 orders of magnitude in terms of airside pressure drop. So when we talk about design here, we really want to focus on all of the mechanisms by which we can explore this design space for heat exchangers without having to spend all of our time evaluating concepts that are not going to be suitable for our application, and really focus in on the best designs. So I want to move this into the direction of how this applies to small diameter tubes. As we've mentioned, the use of simulation tools is really fundamental in doing design work in modern times. If we want to evaluate these kind of heat exchangers, we want to use software to model them before we go and construct them. So this existence of accurate modeling tools is really kind of the foundation of what's going to allow us to do this design work. We need to be able to simulate a heat exchanger accurately with these 5 millimeter tubes and know that the results we're getting on the computer are going to match with what we see in the lab. Otherwise, there's limited value in doing this kind of modeling. So we need to have accurate tools to predict the performance before we can get started and actually do the design work. As we discussed in our first webinar, we learned that the airside pressure drop is an important consideration in small diameter tube fin heat exchangers. If we compare a large diameter tube to a small diameter tube at the same velocity, we see that the friction factor is greater in the small diameter tube heat exchanger. And that's kind of visualized here by this larger boundary layer proportionally along the surface of this tube, the small diameter tube. So it's one of the most important considerations we need to keep in mind when we're designing a 5mm or smaller heat exchanger, is that we need to configure the tubes and the fins in a manner that allows us to maintain an acceptable level of airside pressure drop. And we also covered in the first webinar that as we go down to smaller diameters, not only does the cross-sectional area decrease, going from a large diameter to small diameter tube for the refrigerant flow, but also that even at the same mass flux, the refrigerant pressure drop can increase going from large diameter to small diameter tubes. So if we're going to configure a heat exchanger with small diameters, we need to be intelligent about how we pick the circuitry configuration and the number of tubes, so we don't have excessive refrigerant pressure drop that can lead to performance degradation. And then the last three small diameter design considerations I want to cover are refrigerant selection. We may be designing a system that has a particular refrigerant that has limitations on the amount of charge that can be implemented, or the amount of charge that can be included. And when we're going to decide the tube diameter or the type of heat exchanger that's used in our system, we want to keep that in mind, because we know that small diameter tubes can have significant reductions in internal volume, and that may enable us to implement refrigerants that are flammable or mildly flammable, and still maintain safe levels of refrigerant charge. We also want to keep in mind the material cost, which may be reduced when we move to small diameter tubes, which have smaller tube wall thicknesses. And we need to keep in mind all the manufacturing constraints of small diameter tube fin heat exchangers when designing them. And really what I mean there is that we need to develop heat exchanger designs that are based on fin sheets that can be manufactured or are currently manufactured. We need to keep in mind that there are limitations on the bend radii for hairpins and U-bends, and that there are limitations for the minimum and maximum spacing between fins. So all of these need to be factored in when we come up with a heat exchanger design. And these constraints may be new to us if we haven't designed with 5mm tubes before. So moving into the modeling aspect, I just want to cover very basic fundamentals of heat exchanger modeling here. Here on the right side, I have a simple visualization of a heat exchanger. And when we want to model a heat exchanger like this, it's quite typical for simulation tools to break this type of heat exchanger up into a number of segments. So we may take this entire bulk heat exchanger and apply a grid to it, and we can break this heat exchanger into a number of small segments. And then inside of each of those segments, we have tubes and fins, and we can solve the mass and energy balances inside of those individual segments to calculate the outlet state of refrigerant and the outlet state of air for each segment, and iterate that process all the way through the heat exchanger to get the result. And we'll demonstrate this in practice in a moment. But what I want to highlight here is that the fundamentally important thing here in designing, in modeling a heat exchanger, is that we're able to predict the performance on the air side and the refrigerant side, inside and or outside and inside of those tubes accurately. So we need to be able to predict the heat transfer coefficient. We need to be able to predict the pressure drop. We do that with the use of correlations. So it's important that when we look at small diameter tubes as opposed to larger diameter tubes, that we're picking correlations that are acceptable for this tube diameter range. So at this point, I'm going to give a brief demonstration of how we would model a heat exchanger using Coil Designer. It could apply to other modeling softwares as well. But what I want to highlight here is the differences in how we would model a 5mm heat exchanger as opposed to a larger diameter heat exchanger, and provide a few recommendations in terms of the selection of correlations that will lead us to successful simulation. So I have here pictured a 5mm heat exchanger. This is a coil that we actually have out in our lab. It's got 24 tubes vertically. It's about a ½ meter wide. And actually, you can see there's a slight difference. The coil in the picture has 2 rows in depth, and what we're going to model is actually just a 1-row coil. But we have both of these coils in-house, and they're nearly identical. They have 15 fins per inch, and they have a pretty standard tube pattern for 5mm. It's about 19mm vertical spacing. So with that, I'm going to jump into the Coil Designer environment, and we can start to walk through the steps that would be necessary to model this particular 1x24 or 5mm condenser. So I have Coil Designer loaded up on my screen at this point, and I'm going to create a new heat exchanger. And that heat exchanger is going to, of course, be a tube and fin heat exchanger. And as you saw in the diagram previously, where we divide that heat exchanger into a number of segments, we're going to select that we are going to use 10 segments. So we're going to divide each tube into 10 segments. The next step is to enter information about our tubes. As I mentioned, this heat exchanger has 24 tubes, which we call tubes per bank in the transverse direction, and 1 tube bank in the airflow direction. The tube length is, as I mentioned, about ½ meter long, and the tube diameter is 5mm. So I can enter all of this information about the actual tube geometry into the software, as well as the spacing between tubes, which is that standard, more or less standard pattern with a 19mm vertical spacing between tubes, 16.5mm horizontal spacing. And this heat exchanger that we're actually talking about is, it also includes internally enhanced or microgroove tubes. So we can put in the geometry information for those tubes as well. So you can see here a graphic of what the inside of a rifled or microgroove tube might look like. And we can enter the geometry details for all of these features. So here, all of these parameters I have defined in front of me, but I can enter information about those micro fins and how tall and how tall they are and how they're spaced apart. And here I'm specifying that there's 40 microfins inside of that tube. The next step, once the tubes are defined, I'll enter the information about the fins. We have to select which type of fin is being used. It could be a plain fin or split fin. In this case, it's a louver fin heat exchanger. And we can enter the geometry information that's required to define that louver fin. The fin thickness is 0.1 millimeters, and the fin density is 15 fins per inch, as I mentioned before. So the next step is to enter the working fluid or the refrigerant that's used in the heat exchanger. We tested this coil with a number of different fluids, but for now I'm going to focus on a test using R410A as the refrigerant. And the external fluid is just air, moist air. So the final step in configuring this heat exchanger is this most important step of defining the correlations that will predict its performance. So I want to spend some time here to walk through the selection of correlations we would use for this 5mm coil, how they might differ from what we would see in a larger diameter coil. So as we covered before in the first webinar, the airside performance, airside heat transfer is really fundamental in predicting overall heat transfer performance. It's definitely the dominant resistance in most cases. So it's crucial that we get the airside heat transfer coefficient accurately predicted. So we need to predict airside heat transfer coefficient for a louver fin, which is what we selected. So we need to select correlations for a louver fin. And we can see that there are several correlations available in the literature. The traditional correlation from Chang and Wang, which was developed in the early 2000s, was actually developed for larger diameter tubes, around 6 or 7 millimeters and larger, but was never experimentally validated for small diameter tube fin heat exchangers, like in this 5 millimeter diameter range. So instead, we're going to implement this newer correlation from Sarpadar, which is a CFD-based correlation and was developed for smaller diameter tubes from 3 millimeters to 5 millimeters in outer diameter. And it was evaluated experimentally as well at OTS. And you can see throughout the interface now that we've implemented new correlations for this small diameter tube range, not only for this louver fin that we're focused on today, but also for plane fins, for wavy fins, slit fins, and for bare tubes. So we've added this capability into the interface. These correlations are available in the public literature, and these are really the key tool to being able to predict the airside heat transfer and the airside pressure drop for the 5 millimeter coil we're going to focus on today. So I'll select that correlation for airside heat transfer, as well as the same author's correlation for airside pressure drop. The next thing we need to do is define the heat transfer and pressure drop correlations inside of the tubes. And because we entered that microfin geometry, we're going to select a correlation that's appropriate for microfin tubes for the heat transfer coefficient and for the pressure drop for both single phases of the fluid, so the liquid phase and the vapor phase. And then in the two-phase region, because this is a condenser, we need to pick a correlation that's valid for condensers. And it also needs to be valid for microfin tubes. So we'll select the correlation from Koyama for now, which is valid for condensers with microfin tubes. And with that, we're able to view the geometry of the heat exchanger we just created. On the right side, these are the tubes as if they were going into the screen. There are 24 of them. On the left side of the screen is a view of essentially the face of the coil, where airflow is going into the screen, where we can discretize the incoming airflow, air velocity, air temperature coming into the coil. So the next thing we need to do is specify the circuitry for this coil, and we can do that by clicking on the heat exchanger to connect circuits. We can specify inlets and outlets anywhere on this interface. In this case, we just have 2 circuits in the coil. And we can automatically generate these circuits by going to Project and Generate Circuits. And we can implement our 2-circuit geometry into this coil. So from here, we want to simulate the coil under some realistic test conditions to see how accurate is this model. And we took this particular coil into our lab. And here's an example test point that we took from the lab. With the entering air and refrigerant states, and this is using 410A for testing. So I'm going to enter this information into Coil Designer so we can simulate this particular test point. So I'll go to Edit, Air and Refrigerant Inlet State, and I can enter the incoming air temperature, the air relative humidity, and the airflow rate. And then because this is a condenser, we have superheated vapor coming into the condenser. It's convenient to define that in terms of pressure and temperature to define that thermodynamic state. So I'll specify the incoming pressure going into that heat exchanger, which is about 2.7 megapascals. And then the incoming temperature is about 322 Kelvin. The refrigerant flow rate is about 28 grams per second. And we can go ahead now with this flow information and geometry information all specified and simulate the heat exchanger. So here we get our simulation results. We can see the predicted overall heat load, the airside pressure drop across the coil. We can see our outlet refrigerant and air temperatures, along with some summary information about the heat transfer area, heat transfer coefficients that are predicted for this heat exchanger, and some other visualizations of the distribution of charge in the heat exchanger, and even more detailed segment level information about what's going on inside of the coil. So we're going to take this and compare to our experimental results. We took this same coil and tested it in a closed-loop wind tunnel under a number of different test conditions. And here, I mean, very briefly, I can see for this test point that my air pressure drop is coming out quite similarly with about 38 pascals. The overall capacity is coming out similar between the model and the experiment. And here I have some simple graphics just showing the summary of tests that we conducted using R410A, R404A, R407C to predict the capacity and the airside pressure drop, and comparing those predictions on the y-axis against the experimental results on the x-axis. So this is just a quick demonstration of the performance of these correlations and the use of this model in Coil Designer to predict some experimental results. And we'll be publishing some papers on this in the future to summarize the experimental work that's been conducted to verify these correlations. So from here, I want to move forward to show an application. Now that we've established that we can model heat exchangers with software, and that allows us, that aids us in the design process, I want to walk through some of the steps of an example design problem that we might be faced with. So for this particular problem, I'm going to look at a drop-in replacement for a condenser. This is an existing unit. And this is one of the more, I think, challenging design problems we can be faced with for heat exchanger design. And that's really because we're dealing with an existing system that has established performance, and we're replacing a heat exchanger and constrained to the enclosure and all other components that are included in that system. So it's critical that we maintain the same capacity as the baseline system, that we don't increase the airside pressure drop, or else our operation with that fan may be threatened, and we don't increase the refrigerant side pressure drop. And also, crucially, we can't change the dimensions of the heat exchanger significantly because we're dropping in a replacement to replace this coil. We need to make sure that the new coil is going to fit in that same envelope, or else we'd have to change the design of the entire system, which would be unacceptable. So in this case, we're looking at a baseline design that has 3/8" tubes, and our goal is to replace that with a 5mm heat exchanger while not affecting any of these other parameters negatively. So we need to maintain the same capacity, same airside pressure drop or similar airside pressure drop, and we can't increase our refrigerant side pressure drop significantly. Although I'll note that this refrigerant side pressure drop is quite low in this case, and some marginal increases to refrigerant pressure drop would be acceptable for this system. So we have our problem more or less defined, and I want to think about how we would go through this design process in a very simple manner. So we have several design objectives that absolutely must be, that require attention. One is that we need to maintain capacity, or else the capacity of our system or the COP of our system could suffer. We need to maintain the same airside pressure drop and the same refrigerant side pressure drop. And so with all of these design options on the table, we need to think about a way to move forward and actually start evaluating designs so we can come up with a solution. So as a starting point, I suggest that we pick a very simple path forward to come up with an example heat exchanger that will meet our requirements. In terms of maintaining capacity, we know that the overall capacity of a heat exchanger is going to be determined by its heat transfer area and its heat transfer coefficient. We know that largely the airside heat transfer coefficient is dominant in these applications. So, and we learned from our first webinar that the airside heat transfer coefficient of the smaller diameter tube heat exchanger is typically going to be greater than the airside heat transfer coefficient of a larger diameter design. So with that in mind, we can expect that if we maintain similar surface area in our new design to the baseline design, we'll at least have the same performance as our baseline. And we may even be able to reduce it further because of the improved heat transfer coefficient of the small diameter design. With the refrigerant pressure drop as a starting point, just to come up with a design, I suggest that we start off with a number of circuits that would maintain the same mass flux as our baseline, or similar mass flux. And this is really just a starting point that allows us to get a model that we may be able to simulate and learn from, and then further refine. And then as we go into that refinement phase, We know that we expect that our heat exchanger with 5 millimeters may perform better than the baseline design in terms of capacity because of the improved heat transfer coefficient and the similar surface area. So we may be able to reduce the material further to reduce material consumption or reduce the size of the coil. With the refrigerant pressure drop, there may be refinements to the circuitry that are possible. We could add or remove circuits to improve performance. And in terms of airside pressure drop, we can start studying the effect of fin density changes and tube configuration changes to ensure that we achieve a refrigerant pressure drop that's acceptable. And in this phase, there can be a fair amount of trial and error as we look at all of these different configurations of different fin and tube configurations, different circuitries, different numbers of tubes. And it's really, I think, we'll see that it's really very helpful to be able to automate and parameterize this process. And when we can use optimization algorithms to do this process for us, we can make sure that nothing's left on the table. So as just a very simple first step, we need to first lay out an example heat exchanger that could replace this 3/8-inch tube heat exchanger. We know the baseline has 2 by 22 tubes and the vertical spacing is about 1 inch. But with a 5 millimeter design, a typical vertical spacing might be more like 19 millimeters. So we can fit, I think, a little more than 29 tubes vertically in that same space. We'll select 28 tubes because that gives us an even number, which is helpful for circuiting. So we can place 28 tubes vertically in the same space as what we could only fit 22 tubes in for the 3/8-inch tube. And this is just a visualization to kind of show the scale of that, how much smaller the 5 millimeter tubes are than 3/8, and how many more tubes we're able to fit into the same vertical space. And the next item we need to consider, as I mentioned before, is maintaining the surface area of the baseline design. So using Coil Designer, I was able to model and simulate the baseline heat exchanger. And I find from that calculation that there's almost 23 meters squared of surface area on the baseline coil. So if we had a 2 by 28 row 5 millimeter design, that actually requires to have 24 fins per inch to match the same surface area as the baseline. And we can see that visually, that when we look at the 5 millimeter design, because of that smaller vertical and horizontal pitch, the fin sheet of a 2-row 5 millimeter design is much smaller than the fin sheet of a 2-row 3/8-inch design. So if we're going to achieve the same surface area, it makes sense that we need more fin sheets or a tighter fin density in order to reach that higher surface area. But we can also imagine a 3-row design with 5 millimeter tubes where we have 3 rows in the airflow direction. And because that gives us more depth in the airflow direction, we're able to achieve the same surface area as the baseline with just 16 fins per inch. So both of these are viable options that we can consider that would give us roughly the surface area that we're looking for and fit within the enclosure that we're focused on. So moving forward, we need to look at the circuiting. Now our baseline design has just 2 circuits. Under some typical operating conditions, the mass flux is about 167 kilograms per meter squared second. And we can see visually, if we just look at the cross-sectional area of the 3/8-inch tube compared to the 5 millimeter tube, the flow area of the 5 millimeter tube requires that we have close to 3 3/4 5 millimeter tubes for every 3/8-inch tube to match the same refrigerant flow area. So when we look at a number of circuits that would match our mass flux of the baseline, it works out that around 7 circuits gives us a similar mass flux to what we see in the baseline. And you can see the mass flux is a little bit higher. We also know that the smaller diameter tubes may have higher pressure drop even at the same mass flux. So this 7-circuit design would be expected to have a little bit higher pressure drop, but should be comparable and should be a good starting point because 7 circuits divides very well in our 28 tube configuration. So with this in mind, we have a starting point for heat exchangers, and I went ahead and put these into Coil Designer to simulate them. And I found that this 3-row design with 16 fins per inch It has a 27 Pascal airside pressure drop, so it matches almost exactly with our baseline coil. So this would be an acceptable design right off the bat from selecting something that has the same surface area and fits in the same space. We also find that the capacity is actually increased in that design. So there may be some opportunity to reduce the fins to further reduce the costs or improve the performance of the cycle. And with our two-row design, with 24 fins per inch, we run into a little bit of a challenge where we have a higher airside pressure drop. It's increased by, I think, about 35% as we go from the baseline to this 5mm heat exchanger. And that's because of this very high fin density that we're using. So one thing we might want to consider is what happens if we're able to reduce the fin density of the two-row design and increase the airflow rate to match the performance of the baseline. So I'm going to show a couple of these results in tabular form. I think it makes it a little more clear. If we look at our three-row design with 16 fins per inch, we can operate at the same airflow rate and we get the same air pressure drop as the baseline. Our capacity is increased by 2%, which is helpful, but our refrigerant side pressure drop is increased by 40%. Now, in this application, I think this is an acceptable increase in pressure drop. It doesn't degrade the COP of a cycle using the heat exchanger significantly, and that's because the refrigerant side pressure drop of the baseline is very low, so we're still looking at about 10 kilopascals of pressure drop. But we could also explore designs that may have 8 circuits or 9, or take this further into further refinement to come up with a configuration with less refrigerant pressure drop if that's required. But what's impressive about this design already is that with very little effort, we've come up with a configuration that is reducing our tube material by about 40%, reducing our fin material, and the internal volume inside of the tubes is cut in half just about, which is going to determine our refrigerant charge in the heat exchanger. So we can expect a big reduction there in the amount of refrigerant as well. I've simulated this same design with 14 circuits just as a kind of a more extreme upper limit of reducing the refrigerant side pressure drop. And in this case, we see, again, acceptable performance in all these parameters and significantly reduced refrigerant side pressure drop. So you can imagine that there are other designs that are worth exploring that may have different circuitries between these two parameters, between 7 and 14 circuits, that would also give us good performance with the 3-row design. And then when we look at our 2-row design, as I mentioned before, we have an increased air pressure drop and increased fan power. The capacity is acceptable, or refrigerant pressure drop is acceptable, and we're able to reduce the tube material consumption by about 60%, and the internal volume of the tubes is decreased down to just 34% of the baseline internal volume. So this is a very attractive design, going down to just 2 rows with 5mm tubes, but we have this challenge of the increased fan power. It should be addressed. And as just a starting point, as one possible configuration that we could consider, I look at what happens if we were to increase the airflow rate and decrease the fin density. So if we go down from 24 fins per inch down to 17 fins per inch, here's a design that is able to accommodate more airflow rate at still a lower airside pressure drop than the baseline. It has a lower fan power than the baseline. So there's some more room for optimization and refinement here, and still has acceptable capacity, refrigerant pressure drop, and we're able to make use of this 2-row design that's significantly reducing our material consumption and our internal volume. So all 4 of these, I think, are viable designs in varying applications depending on the requirements. But I think we've shown here that with relatively simple design work, not too much effort had to go into this. We could come up with designs with 5mm tubes that replace a larger diameter heat exchanger without negatively affecting the system, but also can give us significant gains in material or cost reduction and potentially charge reduction. To take this one step further, we see that there's a number of options we might want to consider in looking at the different configurations of airflow rates, different fin densities, and tube configurations, and it would certainly be time-consuming to explore them all by hand. even with the use of software. So I want to just kind of briefly introduce the idea of using optimization in solving a problem like this. In this case, we focused on a very similar study. This is an almost identical heat exchanger that we optimized. It also requires the 4 kilowatt heat load. It operates under operating conditions that are the same. And we use optimization variables here, or we define these optimization variables that make up the entire design of the heat exchanger. So we looked at different tube pitches in the longitudinal and transverse direction, different numbers of banks and fin densities. We explored slit fins and louver fins. We looked at a number of tube banks from 1 to 5 and 16 to 32 tubes vertically, different numbers of circuitry configurations, different numbers of louvers and slits, and really developed a very wide design space for potential heat exchanger designs. And what we did with this is this problem definition is apply a multi-objective genetic algorithm solver to solve this problem for us using heat exchanger modeling software to predict the performance of each candidate design. So just as a graphic here, I'm showing on the right-hand side a visualization of what that process might look like if we look at a genetic algorithm solve a problem through each iteration as it learns from one to the other, how different design parameters affect the performance of a heat exchanger. We see that each of these points, which represents a heat exchanger, is slowly improved as we reduce the material cost and the airside pressure drop in this example. This is just a visualization of what that might look like as the solver would seek out more and more optimal designs. From the result of this study was really this plot, which is summarized in an ASHRAE paper that we distributed as part of the webinar series. But this, I think, illustrates some of the strength of the optimization process in that it took us a fair amount of time to come up with a design by hand, although it was not very challenging. We're always left with the question of what is left on the table, how much can the design be improved? And by using multi-objective genetic algorithm solver, we're able to simulate thousands of designs, in this case ranging from 3 millimeters to 3/8 of an inch, and find the optimum designs in terms of minimizing material cost, minimizing pressure drop, minimizing refrigerant charge, so we can select heat exchanger configurations that we're more confident are the best possible design for that application. So this is one of the great strengths of using modeling software, simulation tools, that we can apply these types of optimization algorithms to solve the problems for us without having to expend a great amount of engineering time to solve them. So I want to quickly wrap up the webinar series at this point. We learned in our first webinar about some of the fundamentals in terms of heat transfer and the physics that are involved in small diameter tube fin heat exchangers. If we take a closer look at a coil, we see the microgroove tubes, which because of their lower wall thickness have less material consumption. Their internal enhancements allow them to have increased refrigerant side heat transfer. And because they're smaller tubes, we're talking about smaller diameter tubes, we see increased air side heat transfer. And we see the same types of things with the fins. We have the ability to implement a number of different enhancements on the air side on these fins. With smaller diameter tubes, we see higher fin densities, and we see higher heat transfer coefficients on the air side as well. We learned in the second webinar about the manufacturing process of heat exchangers, of tube fin heat exchangers. And we saw that in particular when we're looking at small diameter tube fin coils, it is possible to expand these tubes using mechanical and pressure expansion techniques, and that there's equipment available specifically for small diameter tubes for doing tube insertion and fin stacking tasks. And then from our design presentation, hopefully we learned that the design process is aided significantly by using simulation tools. We can use optimization to solve more challenging problems for us, and that fundamentally we really need to focus on the airside pressure drop in a design, and we need to select our fin and tube arrangement accordingly, and that because of the smaller diameter of these tubes, we need to intelligently select a circuiting design that doesn't increase refrigerant pressure drop to an unacceptable level. So as far as next steps for the webinar series, we'll be distributing surveys following this presentation, and we ask for your feedback. There'll also be, as I mentioned, a question and answer summary sheet that includes all of the important questions and answers that we've covered in each of the 3 webinars, and we'll send that out by email. We hope you'll take the time to download a copy of the Coil Designer demonstration version, and you can use that for evaluating 5mm heat exchanger designs on your own. And if you're interested in receiving a sample 5mm heat exchanger, we just ask that you complete the surveys for all 3 webinars. If you weren't able to attend the first 2 webinars, we ask that you review those videos and based on what you learned from those videos, fill out those first 2 surveys and provide us with your contact information, and we'll be in touch to provide a sample heat exchanger to you. So at this point, we'll take some time for questions and answers. I'll just pause for a moment and review the questions that we've received. And again, if you have questions, feel free to submit those using the chat feature in the GoToMeeting interface. So we don't have any questions coming in so far. We'll stay on the line for a bit and definitely encourage you to submit your questions as they come up. We did receive one question asking about which manufacturers which manufacturers use 5mm heat exchangers in their coils. I don't think I can really comment on that to disclose any manufacturers' specific use of materials, but I think there are a number of major HVAC suppliers, OEMs, that are using small diameter tubes, particularly 5mm. So there was one question about entering refrigerant side conditions in Coil Designer. We do have the ability to solve for outlet conditions instead of inlet, or specify the refrigerant state at the inlet in different terms, in terms of vapor quality and pressure, for example, instead of pressure and temperature, or solving for an outlet subcooling. And you can find out more about that if you look up our YouTube channel. We have some tutorials for using Coil Designer. There's another question about bimetal corrosion between copper tubes and aluminum fins. I'll admit to you that I'm not the materials expert here, but these types of coils are implemented in a number of heat exchangers worldwide, and that challenge has been overcome by a number of manufacturers. I believe that type of corrosion is not a significant challenge or a game-changing challenge for these types of heat exchangers. There was another question about tube sizes less than 5 millimeters And there are certainly manufacturers out there exploring smaller diameter tube fin heat exchangers with 4 millimeters and 3 millimeters. And we have shown in simulation studies that these types of these diameters do continue to increase performance of a coil, so that there's definitely a good deal of performance potential still available in reduced diameter tube fin heat exchangers, as well as continuing to reduce the diameter even further and looking at sub-millimeter heat exchangers without fins have the potential to improve performance as well. So this trend of improved performance with reducing diameters is consistent and extends beyond 5 millimeters. Yeah, again, there's a question about which manufacturers will be more likely to develop these smaller than 5 millimeter copper tube heat exchangers. And again, I don't think I can comment on the R&D intentions of any manufacturers in the industry, but there are certainly major companies out there exploring these designs actively at this time. And in fact, I think I could say that there are manufacturers in the world that are producing 4 millimeters already at this time. Another question that came in is regarding the selection of correlations within the Coil Designer software. We do have an interface within the tool that allows you to find information about each of the correlations, and this can be used to make selections of an appropriate correlation. If, for example, I pick the correlation that I selected today for liver fins, I can see a paper that was published that details the process for developing this correlation and provides the applicable range of tube diameters, tube banks, all of the geometry parameters of the heat exchanger, and the air velocities for which this correlation was developed. And we can do this same process for other correlations in order to learn which correlations would be appropriate for modeling a particular application. So this is an interface called correlation information that's available within the tool. One more question asks, with all other air conditioning components the same, what is the difference in efficiency between 7, 5, 4 millimeter tubing? It's I think, a difficult question to answer because there's not really a fair way to compare designs of this type. You can imagine a large diameter tube heat exchanger that's much larger, performing very well. You could come up with any number of configurations of 7, 5, 4 millimeter heat exchangers, so there's not really a basis to compare them fairly. But we have shown that there are significant improvements in terms of heat transfer as we go down in smaller diameters. So we could look at, on the basis of comparable volume, comparable heat transfer area, we can certainly see improvements from one diameter to the next. But it's a little more difficult of a problem to really quantify that into a single number of how much each diameter performs compared to the other. All right, so it's now 5 p.m. It looks like we've received all the questions we're going to get at this point. But if there are other questions, certainly encourage you to reach out to us by email after the webinar is over. And we thank you for your participation and hope you'll contact us with your survey responses and stay in touch in the future. So thank you all. Have a good afternoon.